This is a video on Snell's law, which is part of the Year 11 physics topic, waves and thermodynamics. Snell's law. So let me just draw a diagram here. So let's suppose we've got two mediums. We've got air, and you've got another medium here, which is water. Okay, two different substances. You've got this imaginary line called the normal that's perpendicular to the boundary between the air and the water, right here. Suppose you've got an incident ray of light, so a light ray coming in. Okay, incident ray. It makes some angle, let's call it theta sub I, with respect to the normal. That's called the angle of incidence. And you've got, so when the incident ray makes its way through the water, so it hits the water, it actually bends towards the normal. Okay, it makes some angle, theta sub r, with respect to the normal. That's called the angle of refraction. Okay, refraction just means, a fancy way of saying bending of light. Okay, that's the refracted ray. Okay, why does it bend towards the normal? Well, because water is actually denser than air. Okay, so light actually slows down in heavier, denser mediums. A good analogy to think of is a swimming pool full of water and a swimming pool full of jelly, right? It's easier to swim in the swimming pool of water than it is the jelly because the jelly is denser, right? It slows you down. Same thing with light. I'm going to show you how to derive Snell's law, okay, as simply as possible. So consider two different mediums here with refractive indices. Let's call it n sub 1 for the air and n sub 2 for the water. So refractive index is a measure of how fast light travels in a substance compared to that of vacuum. Okay, the refractive index of vacuum, okay, so empty space is just 1. Okay, that's the standard that we set. Anything greater than that means that the medium is dense. Anything less than that means that the medium is less dense, right? So a higher refractive index, high density medium. Diamond, for example, would have a higher refractive index than water, okay, because it's denser. Okay, so we've got two refractive indices there. We've got an incident ray of light traveling from the first medium, the air, to the second medium. And let's call, so the theta sub I, I'm going to call that theta sub 1 by convention. And the refracted ray, theta sub r, I'm going to call that theta sub 2. Now, the speed of light in each medium is inversely proportional to its refractive index. What that means is, so speed of light is c. It's actually Latin for the word celeritas, which means quick or swift, right? So it's inversely proportional to the refractive index. Let's call it n. Okay, so if you increase the refractive index of the medium, you decrease the speed of light, okay? And vice versa. So therefore the speed of light in medium 1, so therefore the velocity of light, let's call it v sub 1, is just c over n sub 1. Okay, and the speed of light, let's call it v sub 2, in medium 2 is just c over n sub 2. Okay, we're expressing it as a fraction of the, as a ratio. Okay, we've got the refractive indices in the denominator. Now, according to the principle of conservation of energy, the product of the speed of light and the sine of the angle of incidence remains constant during refraction. Okay, energy can't be created or destroyed, right? It's just being transferred in this case. So, in other words, v sub 1, so in the case of medium 1, okay, the air in this case, v sub 1 times sine theta sub 1 is constant. Okay, the speed of light multiplied by the sine of the angle of incidence remains constant. Where the sine here, so sine, if you recall from maths, is opposite over hypotenuse, opposite over hypotenuse. Okay, that ratio right there. And similarly for medium 2, which is the water in this case, v sub 2 times sine theta sub 2 is constant. Okay, where theta sub 1, theta sub 2, if you recall, angle of incidence and angle of refraction from up here. Now, if we combine these relations here and these ones here, we can come up with something. We get this. Okay, so v sub 1 is c over n sub 1. So let's replace v sub 1 with c over n sub 1. So c over n sub 1 sine theta 1. Okay, because they're both equal to some constant, we can equate them, right? So that's equal to, so v sub 2 is just c over n sub 2 sine theta sub 2. And if we simplify this, we get sine theta sub 1 over sine theta sub 2 is just n sub 2 over n sub 1, because the c's cancel out when you rearrange. And when you rearrange this, you get this relation, which is Snell's law. Very neat way to derive it. Okay, there's different ways to derive Snell's law. I think this is one of the good ways to do it, just logically, using conservation of energy and just using simple maths. And my apologies, just here, where I mentioned that they were constant, they're actually not constant. The product of the speed of light and this angle of the and the sine of the angle of incidence and refraction does not remain constant. Okay, because during refraction, the speed of light changes as it passes from one medium to another. Okay, due to the change in refractive index. So the correct way of saying is rather the ratio of the sines of the angles of incidence and refraction is constant. Okay, which is Snell's law. Right, which is this here.